ratio of our conjugate base to our acid. Sorry? That one's on there. That's the only one on there that's from like the acid-base stuff, which it forms the basis of pretty much all of it. Okay, so what is a buffer? It is a solution that resists pH change. Okay, in the most basic definition. Okay, how? How do we make one? How do we get one? You're mixing together a weak acid, okay, which by definition was something that doesn't dissociate appreciably in water. It has a really low Ka, right? So its acid dissociation constant, right? Its Ka is really low. It will have a pKa value then that is a positive number, since this number is going to be less than 1. Okay? So there was a question that said, could every acid be used to make a buffer? And the answer is no. Okay? Strong acids are not going to work to make a buffer. Okay? We need a weak acid and a salt of its conjugate base. If you put them in at equimolar concentration, so the example we did last time was acetic acid and sodium acetate, and I will show that example again on the next slide for this particular combo. But so at equimolar concentrations, if you were able to mix together equal parts of your acetic acid and sodium acetate, then you could control the pH of your solution, right? It will be the pKa of the acid, okay? So this is specific to each acid, its pKa value. And because of our Henderson-Hasselbalch equation, if these are approximately equal, this goes to 1, this whole piece goes to 0, and pH is pKa. So this is a way to, I want to make a solution that has a particular pH. I want to control the pH of my buffer. I also could change up the ratio of these. You know, they don't have to be equal. If I want to get a particular pH, I might do a particular ratio, whatever I'm trying to make. Okay, so I have control. Why are buffers important? Our cells and our biological tissues require it, okay? We have specific pH requirements inside our cells that we need to maintain, okay? Above or below which we're in a state of acidosis or alkalosis, something, lots of downstream dangerous symptoms associated with that, okay? There's two popular buffer systems in our body, hydrogen phosphates and carbon dioxide bicarbonate. You do not need to memorize these. If I want you to do anything with this, the equation will be provided to you, like on the exam. It'll look like this, and then I'll ask you, you know, what the ratio of acid base to something. If you have so much bicarbonate and so much of this, give me the pH. But the equation will be given to you. You don't have to memorize it. The pKa's would be given. There's no need to memorize any of that. All right. I decided I wanted to pull internet pictures. This is just some poor choices here. All right, so we have acetic acid. Okay, it has a pKa of 4.7, or like I said, a very low Ka, a Ka smaller than 1, so about 2 times 10 to the negative fifth. Here's the basic reaction for acetic acid dissociating into a proton in its conjugate base. And like I said, you would be able to, hopefully, from this, write this. It's an equilibrium constant, right? It's products over reactants. I think you guys can do it. I don't think I'm gonna have it. Here's sodium acetate. I don't know. Here's the reaction for that. So we have sodium and acetate actually bound to each other, and then we put them into water, and they would dissociate or dissolve. We're not gonna have sodium ions, and we're gonna have our acetate ion. And we put them in water. Oh, I don't know what that is. So I mix these together to make my buffer. When I put acetic acid in water, it basically stays as acetic acid, okay? It does not want to dissociate. So even though I put it in water, I basically just have a bunch of this. With sodium acetate, with my salt of my conjugate base, it will dissolve into sodium and acetate ion. So if I mix these two things together, I can have both my acid and my base in a solution. Right? That's what I need to make a buffer. And so the reason this won't work with a strong acid is because a strong acid is going to break down into this. So I'll just have the base half. I won't have the acid half anymore because it will dissociate. Okay, so then the example we did last time was, let's say we have this particular solution, and then we put some hydrochloric acid in. Hydrochloric acid is a strong acid, right? I know, these are horrible choices. I had a weird weekend I didn't feel well. I can't describe it though. It was just like overall body ache, kind of just like a sick feeling in general. And I wasn't motivated to do anything but watch My Cat from Hell on Animal Planet for hours on end. And so this is what happened during that time. Who knows? Whatever. So the Ka of hydrochloric acid is very high, right? It wants to dissociate about 1,000, so it's pKa. We know how we could calculate that. Okay, pKa is inverse log, negative log of our Ka. All right, it's about -7. So again, like I said, this one's going to dissociate. So if you think about putting all three of these things together into water, we have acetic acid as an acid. We have our acetate ion as our conjugate base. And when we put HCl in and it breaks apart, we now have protons around. We have acetate ions around. Those two are going to come together and go back this way. All right, we're going to make more acetic acid. So what we'll have is this will go up, and this, once it recombines with protons up here, will go down. Okay? So there's changes in the acid and base concentrations when we put in HCl. And last time we went through a very simple example of that, and we'll do it quickly again, okay, with the math. So, what are you laughing about?
Acetic acid, honestly, is what he said.
Yeah, why don't you put more acetic acid back in there?
Because it will just break apart. I'm sorry. Yes, you could put acetic acid in, but in reality, I'm not talking about situations where like I want to change the concentration of my acid to base in my buffer. I want to control the influence of other acid and base chemicals coming into play. Yeah, I would just be controlling my buffer then. I would be changing the pH of my buffer slightly. But this is about how can I resist a pH change from something else happening. Obviously, these are like simplified examples from what we care about biologically. So if I have, consider adding 1 millimolar of HCl to a buffered solution that's equal parts, 5 millimolar each, of my acetic acid and my sodium acetate. In this case, HCl completely dissociates, or assume it goes to complete dissociation. It makes 1 millimolar of protons, so you will increase the concentration of the acid by 1 millimolar and decrease the base by 1 millimolar. Here's another internet picture of that. Once the HCl comes in and splits apart, some of that free acetate ions bind up with the protons and become acid. And so then here's the actual math for that. The top is our base, right? We're always going to put our concentration of our base on top. They both started at 5 millimolar, so the units are missing from this, okay? I have an example problem next that you can actually solve your own. One's in millimolar and one's in molar. Make sure you get them all in the same before you start. Okay? But 5 millimolar minus 1 millimolar, we're reducing the amount of base we have because it's turning into acid, right? Protons are combining. So this one is going up. We have a new pH. When we put in HCl, we expect the pH to drop. Okay? The pH of our equal part buffer was 4.76, or the pKa of acetic acid. It did drop, but not by very much. And that was the goal of our buffer. Okay? Instead of dropping to a pH of 3, which is what HCl in water would do, we'll only have a drop of about 0.18 units. And since this is a log scale, it's quite a big difference. Okay. So this is just a graphical version of that. It's showing the buffering capacity of acetic acid and sodium acetate to HCl versus if you don't have it, how the pH would drop really rapidly. And where this is important is, of course, say in the bloodstream. If some acidic substance or basic substance enters the bloodstream, we have a buffer system in place to resist that change. And that is, like I said, where it really matters for us. Okay?